If you look at a computer from the year 2005, you might notice something unsettling. The processor inside that aging machine likely ran at a speed of 3 gigahertz or perhaps even higher. When you glance at a modern high-end laptop from the year 2025, you will see numbers like 4 or 5 gigahertz. On paper, it looks as if the very heart of our technology has barely moved in over 2 decades. This observation creates a haunting question that lingers in the mind of every tech enthusiast. Has the progress of the central processing unit simply stalled out, or are we being deceived by a single, misunderstood metric? The truth is that performance has continued to explode, but the path of that growth shifted in a way that most people never saw coming. We grew up in an era where a higher number on the box always meant a faster experience on the screen. This was the era of the clock speed myth, a time when raw frequency was the only god the industry worshipped. Today, we're going to pull back the curtain on why those numbers stopped climbing and what really happened behind the scenes. Before we dive into the wreckage of the frequency wars, please take a moment to subscribe to the channel and join our community of deep thinkers. In the early years of the 2000s, the atmosphere in the semiconductor industry was one of boundless optimism. Engineers at the world's largest chip companies were drawing graphs that pointed straight to the heavens. They predicted that by the end of that decade, we would be using processors running at 10, 20, or even 30 gigahertz. It seemed like a natural progression, an unstoppable force of human ingenuity. But amidst the excitement, a small group of researchers began to circulate a presentation that looked more like a warning from a dystopian future. They showed a chart comparing the heat density of a CPU to other well-known objects in our world. At the rate they were going, a processor would soon generate more heat per square centimeter than a nuclear reactor. If the trend continued just a little longer, the silicon would reach the temperature of a rocket nozzle. Eventually, the graph showed the surface of the chip becoming as hot as the sun itself. At the time, many people thought this was a joke, a bit of hyperbole used to spice up a boring technical conference. But the engineers weren't laughing because they knew the physics were cold and unforgiving. They were approaching a physical wall that no amount of clever marketing could bypass. The sun chart was a mathematical certainty if they stayed on their current path of simply cranking up the clock. It was a moment of realization for the industry, a realization that their entire strategy for the future was fundamentally broken. This wasn't a failure of imagination, but a direct collision with the laws of thermodynamics. To understand why this happened, we have to look back at the golden age of the megahertz. In the 1990s and the very early 2000s, increasing the clock speed was the easiest way to make a computer faster. The clock is essentially the heartbeat of the CPU, the metronome that tells every component when to take its next step. If you make the heartbeat faster, the processor completes more cycles every second, and the software runs quicker. It was a simple, linear relationship that everyone could understand. During this time, the industry was locked in a fierce public battle for dominance. Every few months, a new processor would be released that pushed the frequency a little higher than the one before. Consumers were trained to look for that gigahertz number as the ultimate sign of quality and power. It was an era of brute force engineering where the answer to every problem was simply to run the engine harder. This period reinforced a dangerous belief that this trend was a permanent law of nature. As we moved into the mid-2000s, the competition reached a fever pitch. Companies were so desperate to win the frequency war that they began designing chips specifically to hit high clock speeds, even if it meant sacrificing efficiency. They lengthened the internal pipelines of the processors, breaking tasks into tiny microscopic steps so each step could be completed faster. This allowed them to hit the 4 GHz milestone, but it created a fragile system. It was like building a car that could only go 200 miles per hour but stalled every time you hit a small pebble. This obsession with the marketing number blinded many to the long-term consequences. While the clock speeds were climbing, the power required to maintain those speeds was growing at an exponential rate. The industry was effectively trading its future for short-term gains in the present. They were pushing silicon to its absolute limit, ignoring the fact that the more energy you pump into a tiny space, the harder it becomes to get that energy back out. The stage was set for a massive collapse of the status quo. The heat wall finally arrived with a vengeance, and it wasn't a subtle transition. Suddenly, high-end desktop processors were consuming massive amounts of electricity and requiring cooling systems that looked like car radiators. Some chips became so notorious for their heat that users jokingly used them to fry eggs or warm their rooms during the winter. But for the engineers, it was a nightmare because the heat was starting to physically damage the components. The leakage of energy was becoming so great that the chips were effectively melting themselves from the inside out. The problem was no longer about how fast the transistors could flip, but how much heat the cooling fans could carry away. We had reached a point where doubling the speed would require quadrupling the cooling capacity, which was impossible for a consumer device. No one wanted a computer that sounded like a jet engine and tripled their monthly power bill. This thermal sealing was the end of the line for the frequency-first philosophy. It was a hard reset for the entire world of computing. To truly grasp the tragedy of the clock speed failure, we have to look at the math that governs electricity. The power consumption of a chip is roughly proportional to the voltage squared, multiplied by the frequency. This means that if you want to increase the speed, you almost always have to increase the voltage to keep the signal stable. Because the voltage is squared in the equation, even a small bump in speed leads to a massive explosion in power draw. This is the power wall, and it is an unyielding master. For decades, we relied on miniaturization, making transistors smaller to counteract this effect. Smaller transistors generally require less voltage, which allowed us to increase the clock speed without the power getting out of control. But as we reached the scale of mere atoms, this trick stopped working as well as it used to. We were packing so many billions of transistors into a single square inch that the total heat density became unmanageable. The math had finally caught up with us, and the free lunch of frequency scaling was over. But there was another, even more insidious problem lurking in the shadows: leakage current. In the old days, when a transistor was off, it stayed off and consumed almost no power. But as transistors became microscopic, the layers of material became so thin that electrons began to tunnel through them like ghosts passing through a wall. This meant that the chip was leaking electricity and generating heat even when it was doing absolutely nothing. It was like having a faucet that you could never fully turn off, slowly draining your resources. By the year 2004, the industry realized that the old strategy of faster clocks was dead. The leakage was too high, the heat was too intense, and the power gains were vanishing. There were no more clever tricks left in the bag to keep the frequency climbing safely. The world's leading chip designers had to make a choice: continue chasing a dead-end dream or find an entirely new way to define performance. They chose to pivot, and that pivot changed the course of human history. The new philosophy was simple in theory but incredibly difficult in practice. If you cut and make one worker go faster, hire more workers. Instead of trying to build a single core that ran at 10 gigahertz, engineers decided to put multiple, slower cores on the same piece of silicon. These cores would run at a more manageable frequency, staying well below the heat wall while still providing more total computing power. This was the birth of the multicore era, the moment we stopped building faster engines and started building fleets of trucks. This transition was framed to the public as a massive upgrade, but it was actually a strategic retreat from the laws of physics. It was an admission that we could no longer win through raw speed. We had to win through parallelism, the ability to do many things at once. This shift allowed performance to keep growing, but it shifted the burden of speed from the hardware engineers to the software developers. It was a new world, and not everyone was ready for it. Interestingly, multi-core processors weren't actually a brand new invention at the time. They've been used for years in high-end servers and supercomputers that handled massive amounts of data. The challenge was bringing this technology to the average consumer at a price they could afford. The turning point came when Intel famously canceled its next-generation high-frequency chips and decided to build its future on a more efficient design originally intended for laptops. It was a massive corporate gamble that paid off, proving that efficiency was the new king of silicon. This move toward efficiency led to a remarkable comeback. Even though the clock speed stayed relatively flat, the processors became significantly more powerful. They did this by improving instructions per clock, or how much work a CPU can get done in a single heartbeat. By refining the internal logic and making the paths more efficient, a modern chip at 3 GHz can do 10 times more work than a 2005 chip at the same speed. It proved that it's not about how fast you move, but how much you carry with you. However, as soon as the industry solved the heat problem with multiple cores, a new set of hidden costs emerged. When you have 4, 8, or 16 cores all trying to work on the same task, they have to talk to each other. They share the same memory, and if one core changes a piece of data, every other core needs to know about it immediately. This is known as cache coherence, and managing it is one of the most complex tasks in modern engineering. It is like a group of people trying to edit the same document at the same time without overwriting each other as work. This coordination takes time and energy, creating a sort of communication tax on performance. If you have too many cores, they might spend more time talking to each other than actually doing work. This is the reason why a 64-core processor isn't 64 times faster than a single-core one for most tasks. There's a diminishing return to adding more lanes to the highway if the traffic is all trying to go to the same exit. We traded the heat wall for a communication bottleneck. This bottleneck is often compared to road congestion. Adding more lanes to a freeway can help move more cars, but if everyone is trying to get to the same office building, the bottleneck just moves to the parking lot. In a computer, that parking lot is the system memory. No matter how many cores you have, they are all limited by how fast they can get data from the RAM. Hardware designers have created incredibly complex interconnects and massive layers of cache memory to hide this, but the fundamental limit remains. While the hardware world was navigating these physical limits, the software world was entering what many called the pain zone. For decades, software developers had enjoyed a free lunch. They could write inefficient code, and the next year's faster CPU would automatically make their program run better. But the multi-core revolution ended that. Suddenly, if you wanted your software to run faster on a new computer, you had to rewrite it to use multiple threads. You had to manually break your program into pieces that could run in parallel. This is much harder than it sounds because most human logic is sequential. We think in terms of step A, then step B, then step C, trying to figure out how to do step B and step C. At the same time, without them interfering with each other, is a mental nightmare. If step C depends on the result of step B, you can't run them in parallel. This reality meant that many programs simply didn't see any benefit from the move to multicore for a very long time. In the world of parallel programming, the most dangerous enemies are things called race conditions and deadlocks. A race condition happens when two cores try to change the same variable at the exact same time, and the result depends on which one gets there first. This leads to bugs that are nearly impossible to track down because they might only happen once every 1,000 times the program runs. A deadlock is even worse. It's when Core 1 is waiting for Core 2 to finish, but Core 2 is also waiting for Core 1. The entire system just freezes, locked in a digital standoff. These problems are so difficult that they have changed the very nature of computer science education. It's no longer enough to know how to write a loop. You have to know how to synchronize memory and manage thread safety. This complexity is why your favorite video game might still struggle to use all 16 cores of your expensive processor. Writing stable, parallel code is arguably one of the hardest intellectual challenges humans have ever faced. It is a struggle of logic against timing. Because of this difficulty, the world of software took a long time to catch up to the hardware. For a decade, we had powerful multicore phones and PCs that were mostly running single-threaded applications. It's only in the last few years that modern game engines and professional creative tools have truly mastered the art of spreading their workload. We are finally living in the world that the engineers envisioned in the year 2005, but it took an incredible amount of software sweat to get here. Where does that leave us today? We are in a state of delicate balance. We have accepted that clock speeds will likely hover between 3 and 6 GHz for the foreseeable future. Instead of chasing pure frequency, we are seeing hybrid designs processors that have some big powerful cores for heavy tasks and many small, efficient cores for background work. Your smartphone uses this trick to stay cool while still feeling snappy. Single-core performance still matters immensely for everyday feel, but core count is where the heavy lifting happens. The story of the CPU is a story of human ambition colliding with the stubborn reality of the physical world. We wanted to go faster and faster in a straight line, but physics told us no. Instead of giving up, we found a way to go broader, to work smarter, and to find efficiency in places we previously ignored. It is a testament to our ability to adapt when we hit a wall. We didn't stop progressing. We just stopped taking the easy path. When you look at your life, you might find your own heat walls. Sometimes pushing harder in one direction no longer yields results, and you find yourself burning out without making progress. Perhaps the lesson from the CPU is that when you hit a physical or mental limit, the answer isn't to force it. The answer might be to pivot, to find a way to delegate, to work in parallel, or to focus on efficiency rather than raw speed. Growth doesn't always have to be a straight line upward. Sometimes it's about expanding your reach. Thank you for spending this time with us, exploring the invisible forces that shape our digital world. If you found this journey through the history of silicon thought-provoking, please subscribe to the channel and share this story with someone who appreciates the beauty of engineering.